You're going. Okay. All right. So today we're going to start putting it into gear a bit, and my aim is to cover 2 sections of the book per day, so I'm going to cut out a bit of material. And I'm actually going to reorder. I've been basically going through the book in the way that the book presents it, but this, for the next couple of weeks, I'm going to shuffle material around, and again, I'm going to put on the website which sections of the book that I'm going to cover each day. But I just don't like his organization of the upcoming material. So we are going to go ahead and go into the next section though, and what we're going to start with is Dirac's Spike, which is my own personal name for the Dirac delta function, which you're all familiar with. Okay? Now you should all be somewhat familiar with the Dirac delta function in various contexts, but have you seen it derived? Have you seen it emerged or converged upon by certain sequences? And what we're actually going to develop the Dirac delta function for is not so much for it itself, but for use in a later part of the story, which I'll tell today. So we're going to get started though with the delta function, and you should all be familiar with 2 of the defining properties of the delta function. That is, if I do an integral of a function of x producted with the delta function over dx, then this should give me the value of the function at x equals 0. And of course, this has 2 immediate simple consequences. The first of is if the function that I put in here is 1, then Joel,
1.
It should give me 1, exactly. Alternatively, if I don't like 0 that much, and instead I shift the argument of my delta function by x prime, then what should that integral give me? Jacob? Say again?
The value of f x prime.
Yeah, the value of f at x prime. Oh, sorry. We're integrating over x prime.
Oh, at x.
Yeah, it is. Okay? So in a sense, this is the most general way to define the delta function. But you could always redefine your coordinate system so that the value of x you're entertaining is at x equals 0, and then you can reduce to this more simple definition. Okay? Now, we call the Dirac spike the Dirac delta function. Ross, what's wrong with calling it the Dirac delta function?
Because it's not really a function since it has an undefined value at 0.
Yes, it is not actually a function. What kind of mathematical entity is it?
Scientists.
Say it louder.
Distribution.
It's a distribution. I heard a couple of different voices saying it. This is actually a distribution rather than a function. But it can be limited to by a function. So first of all, let me give you an idea of what the Dirac function would look like if you tried to graph it. And again, I'm going to start out with something in the way of a review, and then we'll turn into a story of the Dirac function with which some of you might not be that familiar. Okay, so we have, we're going to talk about functions of x. This is x equals 0. And you can imagine that if the function f was something like that, then what we want is for the Dirac delta function to be 0 everywhere except at x equals 0. And how high do we want it to be at x equals 0?
Technically infinity.
Say it again?
Technically infinity.
Infinity?
Yes.
Well, if you integrate it, you get 0, and you get 1, and then that's the infinity does. I mean, it's undefined technically, but
Yeah, so the answer is actually infinity, but let me argue that that's the case. You're absolutely right. That's an excellent answer. It's an excellent answer. So let me just imagine what's going to happen here. So if I imagine doing the integral of the product of this function with the delta function. First of all, what's the contribution to the integral from regions over here? It's 0 because the delta function is 0 over here. So 0 times something non-zero is still 0. So the contributions to the integral everywhere except for at x equals 0 is 0. Now if I think about the contribution at x equals 0, I could imagine doing a Riemann sum of rectangles, okay, where the width of the rectangle is dx, which we of course take to 0. What is the height of the rectangle?
0.
Infinite.
Oh.
It's f of 0 times delta at 0. It's the product of the delta function and the function that we're trying to evaluate. Okay? So the total is f0 delta 0 dx, and we want this to give us f0. Okay? Well, if dx is going to 0, what does delta of 0 have to become? It has to become 1 over 0, which is infinite. Okay? Everybody on board? Okay. So this is clearly not a function for a couple of good reasons. One, it's infinite at a certain point, but it's only at x equals 0 that it's infinite. Okay, but it is well behaved as a distribution. Now, none of this is that important for what we want to talk about. I mean, it is, but it isn't. What we're really interested in is realizing this delta function as the convergence of a sequence of regular functions. So we would like to give you some regular well-behaved functions, a sequence of them, so that means they'll be indexed by n, so maybe we have gn of x. And then we want it such that as the limit is taken, and the limit could be in different forms. You might be taking n to 0, or you might be taking n to infinity. It turns out in the book there's examples of both sequences of functions as the limit of n goes to 0 that approach the delta function. There's also an example as n goes to infinity. We're going to focus on the one that n goes to infinity for later reason. But what we're interested in is a sequence of functions such that in the limit on n, this sequence converges to the delta function. Okay? And the good thing about this is these are just regular functions. It's just their ultimate limit is the delta function. Okay. So, now, how can we relate this definition of a delta function to the limits of functions? Well, we've got two options. One, we can say that the limit as n goes to 0 and infinity of delta n of x equals 0 for all x not being 0. Okay? That seems like a good criterion that this needs to satisfy if it's going to limit to a delta function. And then 2, the limit as n goes to 0 or infinity, depending, of minus infinity, infinity, f of x, delta n of x, dx, will hopefully just give us back f of 0. Okay? Now, if we call, well, first of all, okay, so this is a limit of an integral, right? Limit outside of the integral sign. Now, if I wanted to call the limit of delta nx by the name delta x, and we're going to later prove that that is actually the delta function, does this expression become this expression? Does it? If I give this notation that the limit as n goes to 0 infinity of delta nx equals delta x, does this expression become this expression? Who says yes? Who says no? Wow, you're also vocal in your opinions. You've got strong opinions. Well, I mean, what if I just move this over here?
Can you do that?
Can I do that? That's an interesting question. Can I do that?
I'm guessing no.
Is in what way is it convergent, I guess?
Yeah, Lebesgue integral.
Yes, thank you. Remember, in all of our discussions, if needed, we're going to use the Lebesgue measure for our integration every time. And it's with the Lebesgue integration measure that you can freely swap limits and integrals. If you're doing Riemann integrals, which is what we're usually doing in our explicit examples, then you're not always guaranteed to be able to swap, okay? But remember, whenever needed, we will be in terms of Lebesgue measures, which means that we can interchange these. Now, hopefully, you all see that if this gets swapped here and this is replaced by this, then you get exactly that expression, okay? So it's just one more point where the use of a Lebesgue measure in our integrals is important. Not that we're actually going to do any Lebesgue integrals in this analysis. Okay, now it turns out there are quite a few sets of functions which limit to the Dirac spike, as I love to call it. And again, these examples are given in the book. I think they give 3 or 4 examples where you take the limit as n goes to 0. But what I want to focus on is their last example, which is one where n goes to infinity. Okay? So I want you to consider the following. Delta n of x is equal to Cn 1 minus x squared to the n for x greater than or equal to 0. That's the magnitude of x, and this should make it an x you can actually read. And less than or equal to 1, where n is 1, 2, dot, dot, dot. And it's 0 outside of that. Okay? Now, I'm going to argue that the limit as n goes to infinity of this is the delta function. But we want to prove that. Okay? So let's first of all begin by seeing what these CNs are. So the CNs are such that the integral from -1 to 1 of delta nx dx equals 1. Okay? Sort of a normalization factor of sorts. And so we can actually figure out from this expression and plugging in this what Cn needs to be. So what we find is that 1 over Cn is the integral from -1 to 1 of 1 minus x squared to the n dx. This is even, so we can just rearrange it and make it 2, 0 to 1, 1 minus x squared to the n dx. We can go ahead and simplify this a bit by replacing x with sine of theta. And if we replace x with sine of theta, dx becomes cosine theta d theta. And then we can use 1 minus sine squared theta as cosine squared theta, and this simplifies to 2 integral from 0 to pi over 2 of cosine 2n plus 1 theta d theta. Okay? Where again, n takes the values from 1 to et cetera, et cetera. Okay? All right, so let's bang out a couple of c's just to see what the values are. So if n is equal to 1, what we have is 2 times the integral from 0 to pi over 2 of cosine cubed theta d theta. Okay? This is one you should all be able to do, right? How would you do it? Who knows how to integrate cosine cubed theta by hand? Who doesn't? Okay, so I'm just going to give you I'm not going to write down all the steps are in the notes, but I just want to give you an idea of what you do. You take this and you break it up into cosine squared theta, cosine theta. You replace cosine squared theta with 1 minus sine squared theta. And now you should be able to integrate it, because this is the integral of cosine theta. This is the integral of sine squared theta, cosine theta, which is going to be sine cubed theta. Everybody follow? Okay, the details are in the notes. I just wanted to give you an idea. Because when we go to n equals 2, we're going to have an even higher power of cosine, but you can keep repeating this process. Anyway, the details are written up in the notes. You don't need to worry about it if you don't follow it from the first get-go. But the result of this is 4/3. Okay? Cool. I'm going to write that in a slightly different way. Okay? I mean, 4/3 is pretty, but I want to rewrite it in a slightly different way. I'm going to write it as 2 to the 2 times 1 factorial over 1 times 3. What? What?
That's fine. It didn't make sense before, but now it does.
Okay, good.
Now I get it.
Everybody agrees with that, right? Okay, good. Sorry, I'm just checking. You guys, man, I don't know what to do with y'all. Okay, I'm going to do n equals 2 real quick, and you'll see where I'm going with this in just a moment. So we're going to do integral from 0 to pi over 2 of cosine to the 5th, theta d theta. Again, I go through all of this in my notes, but I'm not going to do it here. This gives me 16 over 15. I know, you're looking at it, you're like, oh my God, that's basically this with some stuff. It's this times 4 over 5.
Yeah.
It's that squared. Well, it's actually this. It's actually 2 cubed times 2 factorial over 1 times 3 times 5. I know. It's getting interesting, isn't it? Okay, so first of all, if I have 1 times 3 times 5 times 2 to the n plus 1, you might or might not be aware, but that can be rewritten in a slightly interesting form of 2n plus 1 factorial over n factorial times 2 to the n. What a headache. Oh, wait a minute. This is kind of related to this in a way, and in fact it is. Cn can be written as 2n plus 1 factorial over 2 to the 2n plus 1 times n factorial squared. Don't worry if you don't get it. You're going to do it on the homework. Okay? But no, the reason I was writing it like this is to understand the pattern that was emerging. And then the pattern, it needed a little bit of rewrite. But anyway, so that's the form of these CNs. Now, I'm not doing this because, well, you'll understand why I'm calculating the CNs in just a moment. Okay, but there's our function, or our form of the CNs. And now, the first question we're going to ask is, okay, this thing has got to do a certain thing as n goes to infinity. So the first question I might ask is, what the hell happens to this when n goes to infinity? Well, what's the answer?
It goes to infinity.
Well, I mean, it's not obvious, so I'm going to discover some properties of this, which are going to be useful later on. Okay, so here we go. leave that reserved on the board. Okay. So if I want to know how Cn behaves as n goes to infinity, so I want to go back to 1 over Cn. I can't believe I just erased this. But anyway. 1 minus x squared n dx. Okay? Now let's start with a simple observation. And then again, like, this is proof method of thinking. This is not like, oh yeah, I figured that out. No, this is people whose work and careers are doing this shit. So it's hard to follow. It's hard to figure out, how did they figure out how to do that? But don't worry, that's all they do. They just sit and prove things. So they get good at it. This is larger than this, even though what I'm about to write seems perfectly useless. Here we go. This is larger than this. Who agrees?
Yes.
Well, do you agree or not?
Yeah.
That is larger than 0. I would say it is.
So 1 over root n is smaller than 1, right? And this integrand is positive throughout the range. If it were negative, and you had this piece at the end that was chopping things down, that you were excluding that end by going to a smaller upper limit, then it could be bigger. But no, this is a positive integrand, so making the interval shorter, okay, is going to make the net result shorter. Okay, so this is bigger than that. All right, now I want you to consider the following function. Okay? And notice that g of 0 is 0. And now let's just take the derivative of this for fun. I mean, why not?
If it's your job. Yeah.
I know. I don't actually know if this is my job. I think it is. Okay? So the derivative is positive over the interval from 0 to 1. Okay? You start out at 0. So what can you tell me about g of x over the interval from 0 to 1? Based on the observation that it starts at 0 and then the derivative is positive over the range from 0 to 1.
Positive value.
It's positive, right. So g of x is greater than or equal to 0, but that means that 1 minus x squared n is greater than or equal to 1 minus nx squared. It's the definition of gx. And you're saying it's positive. Okay? And again, this is for that set of x. Now let's return to 1 over Cn. This is greater than 2 times the integral from 0 to 1 over the square root of 2. Oh, wait a minute. Hold on, it's bigger than this, but this is bigger than that. Oh, shit. We can put this in there. Everybody agree? That's good.
Should that square be square root of n, or is it?
Oh, sorry. It's, yeah, sorry, square root of n. Okay? Well, I can do that integral. Can you do that integral?
No.
Let's do that integral for me.
Can I pull up my laptop?
No, I'm just kidding. You don't have to do it for me. This is 4 over over 3 n to the half. Guess what this is bigger than? Yeah, what is this bigger than, for sure? It's bigger than a lot of things, but it is noticeably bigger than that, okay?
By 4/3.
Huh?
By 4/3 bigger.
By 4/3, different, okay? Now, trust me, I'm going somewhere with this. So in the end, we find that Cn is less than n to the 1/2. Okay? So even though n is going to infinity, Cn will never exceed the square root of infinity. And it's going to be more useful than just that simple observation, but it's a nice observation. Okay? All right. So, okay, so now, yeah, I'm going to erase all of this because I don't think we're going to need it anymore. Now, consider, since delta nx is an even function, okay, this is even, x goes to minus x gives you the same thing, then the integral from epsilon to 1 of delta nx dx is the same as the integral from minus 1 to minus epsilon delta nx dx. But what we can argue, geez, it gets confusing for me when I want to write down an integral sign, but right next to it is the delta sign, so I'm going to do a delta from epsilon to 1. That makes no damn sense. Anyway, so integral from epsilon to 1 of delta nx dx. What is this less than? Okay? What do you think? Which of these should I be using? I want to use functions. I don't want to just use the
I don't think
symbol.
it's less than 0.
Say it again?
I don't think that's less than 0,
You don't think what's less than 0?
that integral.
Well, from epsilon to 1
I mean, if epsilon's greater than 1,
is, well, no, epsilon is less than 1.
yeah.
Sorry.
So it should not be less than 0.
So which of these two should I use? The top one, yes, thank you very much. Sure. Okay, so if we're going to use the top one, then what we can say is that this thing is going to be less than Cn, but Cn is less than 1 n to the 1/2. So let's just replace Cn with n to the 1/2. Okay? And then I need to do the integral of this, but I think I'm going to cheat a little bit. And I'm going to say this is 1 minus epsilon squared to the n times 1 minus epsilon. Okay? Seems pretty reasonable, doesn't it?
What happened?
I don't know. What do you think?
I don't know.
We'll figure it out, man.
Yeah.
Yeah, Josh, could you glue gun?
Figure it out.
I need
Okay.
glue.
No. Here you go. So what I've done, I have replaced the actual integral of this. I replaced the actual integral of that with the area of a rectangle, which is definitely larger than the integral. Okay? And I'll show you what that rectangle is. Okay? That is, the actual integral is the area under the curve, but what we did was we took the largest value of the curve in this interval, which happens at 1 minus epsilon squared over n. Okay, you're going from epsilon to 1. If you go to 1, what's the what's this value? So this is, the function is 1 minus x squared. What is the value at x? It's like it's 1, it's 0. At x equals 1, it's 0. The largest value of this is when x is at epsilon. Everybody on board? Okay? And the length of the rectangle is 1 minus epsilon. The integral under this curve, the area under this curve is obviously less than the total area of this rectangle. So this is equal to the integral of this, but it's definitely less than this times the area of this rectangle. I just want to get an inequality, that's it. So I'm replacing an actual area under a curve with the area of the rectangle that includes all of that area, and a little bit more. Everybody on board? Okay, good. Now, what is this less than? Well, this is a number less than 1. So this is obviously less than that. That's assuming this thing, or that's replacing this with the number 1, which gives you a bigger area. Everybody on board? We good? Okay, just ask a question if you've got one. All right. Now, here we go. Now, it turns out that x to the n with x less than 1 gets smaller faster than n to the k grows. As k goes to infinity. Oh, sorry. No, sorry, as n goes to infinity. Okay, so obviously, n to the k gets bigger and bigger and bigger as n gets larger. X to the n, where x is less than 1, gets smaller and smaller and smaller as n gets larger. The product of these, though, becomes what as n goes to infinity? It becomes 0. Okay? Hold on. Wait. Look at this. N to the 1/2, something to the n. So what is the limit? What is the limit as n goes to infinity of the integral from epsilon to 1 of delta nx dx? It's 0, yeah. Okay? So what this is telling us is that we can make epsilon smaller and smaller and smaller, and this will still be true. Everybody on board? I mean, epsilon was just a number we picked that's less than 1. We can make it smaller and smaller. This is still true. That means that in the limit, as n goes to 0, the contribution to the function that this is converging to is 0 everywhere except where? At x equals 0. Did everybody follow that? So you have to realize, if you took this and you said n was equal to 1 and you plotted it, it wouldn't look anything like a damn delta function. I mean, you know, it'd be something like this. Okay? But in the limit that n goes to infinity, this sequence is getting narrower and narrower and narrower to the point where anything that's not 0 is not contributing at all. Which is what we expect from a delta function. Okay? Now, since delta nx is positive, let me see what I can write. So delta nx, and I'm talking about these, are positive, okay, and continuous. What that means is that the limit as n goes to infinity of delta nx itself is 0 for 0 less, or for x greater than 0 and equal to or less than 1. Okay? But recall that we have this condition that minus 1, 1 delta n x dx equals what?
Well, that's n goes to infinity.
What did we normalize this to? Remember, we picked our Cn, so this would have a certain, it's 1. Okay? So in the end, what we've just demonstrated is that in the limit, as n goes to infinity, the integral from minus 1 to 1 of a function times this set of functions, okay, gives me this function evaluated at 0. Right? Which is what we expect from the functions which converge to the delta function. Okay? Everybody on board? Okay. Now, okay. So the reason I introduced this particular set, this particular sequence, which converges to the delta function, is because it is an integral part of the following story. And this is a story which is owed to Weierstrass. I know.
So we're going to do this full function?
Are we going to what?
Talk about its full function?
Well, he's got a lot of results, but we're going to talk about a result of his, not his function, per se. So this is due to Weierstrass. And here is a theorem. If f of x is continuous on the closed interval from a to b, there exists a sequence of polynomials, which we'll call P and X, such that in the limit as n goes to infinity, the limit of the sequence is the function f of x uniformly. This is saying it converges to f of x uniformly on AB. Oh! All right, this is a theorem. Now the book does a rigorous proof of this, but I'm going to skip that rigorous proof and give you a more heuristic proof, which is still going to be kind of a pain in the butt, but we're going to use this. Okay?
Hey, Alex,
Yes?
isn't this just kind of the statement that a Taylor series exists?
That is so interesting that you bring that up, because I'm going to nail that in a few minutes. But bear with
Okay,
me.
thanks.
Bear with me, okay? I got to zoom through some material to get to that statement, because it ain't. But anyway, all right, here we go. So first of all, for f of x, so I just want to make this following argument. For f of x on AB, imagine that instead we constructed a function h of x minus a over b minus a. And we could call the argument of this z. where this thing actually equaled f of x. Okay? However, f of a is equal to what?
H of 0.
H of 0. F of b
H of 1.
it's h of 1. Okay? So what we can do is we can always take an interval from a to b, and we can redefine the function so that the actual interval is from 0 to 1. That's without any loss of generality. Okay? Conversely, you can take anything which is defined over the interval from 0 to 1 and redefine it in terms of the integral or the interval a to b. Okay, so we're going to work with 0 to 1, but we're not losing any generality in doing that. Furthermore, consider g of z, which is h of z minus h0 minus z times h1 minus h0. Okay? What is g of 0? Don't make me pick a, okay, I'll pick a card. Josh.
Me, Josh?
Josh. Motor? Molar. Joe. What is g of 0?
1.
That's usually a good guess.
So h of 0 is sorry, say it again?
Or just, yeah, just 0.
Yeah, it's 0. What about g of 1?
That should be 0 again.
Yes, 0 again. Okay. So it turns out that in addition to taking the arbitrary interval and redefining it in terms of an interval from 0 to 1, we can also arbitrarily redefine things such that the function we're dealing with vanishes at the boundaries of this interval. Okay? Now here's the important thing. This redefinition, if f starts out as a polynomial, h will be a polynomial in z as well. And if h is a polynomial in z, so too will g of z. Okay? So the bottom line of this is we can consider g of z's on the interval from 0 to 1, where g of z vanishes at the endpoints, and that's with no loss of generality. Okay? Because that's what I'm going to use. It's going to make a lot of the arguments more clean. Okay, so with that in mind, now, so we're going to have g of 0 equals g of 1 equals 0, and we're on the interval, or we're on the, we're on the interval from 0 to 1. Now what we're going to do is we're going to take Pn of z is minus 1, integral from minus 1 to 1, g of z plus t times delta n plus t dt. This is a sequence. Okay? Sorry, this would be z. Okay, this is a sequence. You pick an integer n, and it's going to give you an element of the sequence. Okay? Now, what is the limit is n goes to infinity of p and z. It's g of z. Which is exactly what Weierstrass said. Okay? So we're using the delta function, actually we're using the series that converges to the delta function to define a series which is converging to any function. But this is a series of it's a sequence of polynomials. Now I want you to think about it for a minute, because Madison asked an interesting question. She said, isn't this the Taylor series? It's not. Okay? And I'm going to show to you why. Okay? So before I do that, I want you to realize, looking at this side of this, it's not obvious that this is a polynomial in Z. Because, you know, this function could be, you know, e to the z. It's any function g of z. So why are we guaranteed that this is going to give us a polynomial? Okay, well, we can make the following argument. Since g of z is 0 for z greater than 1 or z less than 0, then we can write that p in z is equal to the integral from minus z to 1 minus z of g z plus t times the delta function sequence. Okay, we don't actually have to integrate over minus 1 to 1 because this function is vanishing when the argument vanishes. Okay? Now, we can rewrite this ever so slightly. Well, I mean, actually, so it vanishes, I should say, it vanishes, so g of z plus t is equal to 0 for t less than or equal to minus z, and for t greater than or equal to 1 minus z. All right? And then what we can do is we can take this expression and we can simply replace t with t minus z. Okay? We're integrating over t, and z is just the argument of this thing. So let's take our integration variable and replace it by an integral over t minus z. And if we do that, what we end up with is the following. Pn of t is equal to the integral from 0 to 1 of g of t times delta n of t minus z dt, which I might remind you is the integral from 0 to 1 of g of t of Cn times 1 minus t minus z squared to the n dt. Is this a polynomial in t? Or sorry, this should be z. It's not t, it's z. Is this a polynomial in z? Yes, it is, because it doesn't matter what function you give me for g. I'm integrating that. That's just going to contribute to the coefficients. Z squared to the n. This is actually going to be a 2n degree polynomial. Okay? So Pn of z is a 2n polynomial. Okay? Now, we're in a position to ask, is this just a Taylor series or is it different? Okay? And in order to explain this, I'm going to work out a couple of these. And of course, the work is a little bit involved. I'm just going to write the answers to spare us some time. But let's do it. Okay. So let's take our g of z to be sine of pi z. Then pmz is equal to integral from 0 to 1 is equal to cn integral from 0 to 1 sine pi t minus z squared to the n dt. Okay, notice this particular function enjoys this property that g of 0 and g1 are 0. Okay, so let me just do these integrals. So this is going to give me, for p1, oh my goodness, so ugly. It's going to give me the following. 3 over 4 pi plus 3 over pi cubed minus 3 over 2 pi times z plus 3 over 2 pi z squared. As promised, this is a polynomial in z. Everything else is just coefficients. And it's a 2 times 1 degree polynomial. Okay? Let me do P2 real quickly. And you should immediately notice something very interesting. For P2, I have 15 over 16 pi minus 15 over 4 pi cubed plus 45 over pi to the 5th plus 45 over 2 pi cubed z plus 15 over 8 pi minus 45 over 2 pi cubed times z squared minus 15 over 4 pi times z cubed plus 5 over 8 pi times z to the 4th. Who notices something interesting? What?
Well, in a Taylor series, your coefficients for the smaller terms are going to remain the same for higher order powers.
Exactly.
This one they're changing.
Let's Taylor series this, okay? If we want to Taylor series it, and this is something you all should be comfortable with, if we call the resulting polynomials from the Taylor series P prime, then we know that P prime of the 0th order is 0 for that particular function. P at the first order, this is P prime, it's just, these are the Taylor series, is 0 plus pi z. P primed at the second order is 0 plus pi z plus 0. P primed at the third order is 0 plus pi z plus 0 minus pi cubed over 6z cubed. Okay? So you'll notice the Taylor series, if you take n larger and larger and larger, you get more and more terms, but it does not change the coefficients for the lower terms. Yes?
Is the Taylor series better at approximating for the lower?
Well, that's an interesting question. Okay? So which one is better, or are they worse, or what? Okay, so here's the nomenclature that first of all distinguishes these two types of limits. A Taylor series has uniform convergence of a series. Okay? The Weierstrass construction has uniform convergence of a sequence okay? If you're converging as a series, then obviously what that means is that you're adding more terms, but you don't want to screw up what's already there. Okay? Versus the sequence, where the sequence you can redefine all the coefficients for each higher order term in the sequence. There's no restriction that everything can remain unchanged. Okay? So when we say that something converges as a series, we mean this little rule that all the coefficients should stay the same for the lower order terms, whereas if it's converging as a sequence, you can be given this headache, where you might have the answer at P3, but to calculate the answer at P4 is a lot of work, because you've got to go back and reevaluate everything. Okay? Now, that should immediately tell you that Taylor series are awesome and Weierstrass sucks.
Yes.
Yeah, I know. Okay, so it actually is wrong. Weierstrass is better because of the following. Okay? Yeah, if you guys need to go, sorry, go ahead and go. Bye, Joe. Here we go. For the Taylor series to be well defined, we have to have all derivatives of all order be well defined. The only thing that Weierstrass requires is that the function be continuous. So what that means is Taylor series good, Weierstrass good. Taylor series bad, Weierstrass good. Okay? All right, so I think we're going to go ahead and end there. I do have one more page of notes, but I'll just tack those on to Tuesdays. Yeah, I'll tack those on to Tuesdays. They kind of roll over.
What's the next homework that you do?
Okay, yeah. So I'm glad you asked that. The next homework is going to be due next Thursday. I'm going to make them due on Thursday so all my office hours line up. Okay? And I would have had it last Thursday, except I was in Georgia. So my apologies for that. Okay?